All right. So welcome back from spring break. I am actually really excited about the remaining kind of lessons in this course because transportation of gases and acid base balance is really such a important part of our jobs as respiratory therapists. So this is this chapter really kind of the main focus. I know we talk about carbon dioxide and how it gets transferred from the tissues to the lungs here, but really probably the main takeaway from this section is the oxygenation piece. It's important for us as respiratory therapists to understand all the different ways that oxygen moves throughout the body, because that is going to help us understand hypoxia and hypoxemia and the best way to treat it for our patients given a specific patient scenario. So, a few learning objectives here. I am going to warn you that this, um, excuse me, this section or this chapter has a lot of math. Okay, so there is going to be math on the exam. There is math on the worksheet. I will let you know which chapters in the respiratory calculations book that you can do to practice the math a little bit more. Historically, we were doing those um, exercises, when this was an in-person class, we were doing kind of those exercises together. I think I'm gonna do a whole separate video um, of going through those calculations, or I might do it at this one of the synchronous. I actually probably will do it at the synchronous session to help you guys that are not big fans of the math get through it. I know you probably are annoyed with me saying this, but it really is simple math. It's the calculation is all the calculations are pretty basic, kind of repetitive, if you will, and it's not super complex how to do the math. So couple practices with it, I think you guys will be just fine. All right. So how is oxygen transported? Oxygen gets transported throughout the bodies in two main ways. The first is it gets dissolved in the plasma. So the first thing that happens after diffusion, it diffuses across the AC membrane, the arterial or alveolar capillary membrane, and it starts dissolving in the plasma. The second thing that happens then is once enough of the hemoglobin is dissolved in the plasma, then it starts binding up, or enough of the oxygen, excuse me, is dissolved in the plasma, then it starts binding up to the hemoglobin. So, a couple of important distinctions to make with oxygen that's dissolved in the plasma. Because it's just dissolved and it's not combined with hemoglobin, it keeps its same molecular structure. Okay, so it's still oxygen, right? So it has a partial pressure then because it's oxygen molecules. So it's the portion of the oxygen in the blood that gets measured as the PO2, the partial pressure of oxygen. So it could be your PaO2, which is your partial pressure of oxygen in the arteries, your PvO2, partial pressure of oxygen in the veins, or yeah. So depending on what vessel it's coming from, it's still giving off a certain amount of partial pressure. Okay. So when we talk about volume percentages, and I don't get too deep in the weeds on this, this is the percentage of that volume of blood that's made up of oxygen. So if I had a 100 milliliters of blood here, okay, say I have 100 milliliters of blood in this tube, okay, and the volume percentage of that blood that's made up of oxygen is like 0.3%. So that equals out then, if this is 0.3%, I don't even know if I could draw 0.3%. It's so very, very, very little. It's such a little amount way down here at the bottom. That's probably not to scale. But that 0.3% is the amount of oxygen that makes up that 100 milliliters of blood. Okay, so if I would do the calculation, do the math out, that will equal 0.003 milliliters of oxygen being dissolved in 100 milliliters of blood. Okay, so that's if you think about it, of that 100 milliliters, less than, such a small fraction, less than 1 milliliter is actually oxygen. Okay, so 0.003 milliliters of that 100 milliliters is actually oxygen. So it's a super small percentage of oxygen that gets transported this way, which always is kind of surprising, or might, if you reflect back once you start looking at ABG values and once you get into your clinicals and you start seeing how often we rely on the partial pressure of oxygen to assess our patient's oxygenation status, it might, you might reflect back on this and be like, wow, that's really surprising we utilize this so much when it makes up such a small percent. And when we get to the oxygen hemoglobin dissociation curve, I'll talk to you about why we can do that. Okay, so the second part is the oxygen bound to hemoglobin. So most of the oxygen then moves throughout the body, greater than 99% of the oxygen moves throughout the body in the red blood cells attached to that hemoglobin. Okay, so if you think about a hemoglobin molecule, they're actually like this. They look like little donuts. There's like, it's not a hole, but it's like a little dent in the middle of them. But on each hemoglobin, there's kind of 4 spots that O2 can bind to. So in each of these 4 spaces, you can have an O2 molecule. And if all 4 spaces of that hemoglobin molecule are bound to oxygen, then you are that hemoglobin is considered 100% saturated. Okay, so your red blood cells contain about 280 million hemoglobin molecules. Okay, and these are specialized in transporting oxygen and carbon dioxide. So carbon dioxide also gets transported this way. So one hemoglobin, like I said, combined to 4 molecules to be 100% saturated. And if it's bound with oxygen, then it's considered oxyhemoglobin. Okay, so the molecular structure of the oxygen molecule changes when it binds hemoglobin. So this molecule here is not just hemoglobin anymore, it's oxyhemoglobin. So we consider these oxygen or these hemoglobin molecules that aren't bound to oxygen, we consider them to be reduced or oxyhemoglobin. Okay, so usually we refer to them as reduced hemoglobin, and that reduced hemoglobin is what is that bluish in color or purple, more purple in color, and that's why we look cyanotic when we're not oxygenating well, because of the reduced hemoglobin. Okay, so each percentage gram of hemoglobin can carry 1.34 milliliters of oxygen. Okay, this is important because as we get to the next slide, we're going to talk about the calculation. So each of these hemoglobins can carry up to 1.34 milliliters of oxygen. So, but typically, we never are truly 100% saturated with our blood that's carried past the lungs, because we have what we call normal physiological shunts that are happening. So when we're talking about a shunt, this is anytime, excuse me, anytime I have an alveoli that gets at O2 into it, but I don't get blood going to it. So blood doesn't pass past this alveoli, it gets shunted around it. So then unoxygenated blood, so this blood has minus O2, doesn't have O2 in it. It is going to travel back to the left side of the heart and get mixed with oxygenated blood. Okay, and reduce the overall percentage. Does that make sense? So you think about it, you're having blood coming in, oxygenated blood that's coming back from the lungs, mixing with some of this blood that gets shunted past the alveoli and doesn't ever come in contact with oxygen. So it comes back to the left side of the heart, not oxygenated, and lowers the overall the percentage. So there's a couple different structures in in the body that cause this shunt. Again, I wouldn't be, crazy wound up about understanding which wouldn't get crazy wound up with like trying to memorize this or stress about this too much, but those structures are called the thespian venous drainage, and then you have bronchial venous drainage. So those are just two anatomical structures that cause this to happen. And also when you have alveoli that are underventilated. So these two structures are kind of describing what's happening here. And then you can also have, try again here. You can also have it happen where you have alveoli that don't get ventilated and the blood that passes past those alveoli never get any oxygen because there's no oxygen for them to pick up. So this blood has minus O2 also. And that's describing that scenario here with the alveoli that are underventilated. So all of those make up normal physiological shunts. So to calculate out how much of the hemoglobin is bound with oxygen, you can take the hemoglobin value that gets reported on the ABGs or on blood gases called CBCs. You can take that value, multiply it by the total carrying capacity, which is 1.34, and then multiply it by the saturation. And that will give you how much is bound to the hemoglobin, okay? So this is going to be the larger portion of the oxygen that's transported. It's going to be transported this way. Then you can calculate out that small percentage that's transported, dissolved in the plasma, by taking the partial pressure of the oxygen dissolved in the plasma and multiplying it by the 0.003. And this is the stuff that's dissolved in the plasma. So bound hemoglobin, dissolved in the plasma. And that will give you your total oxygen content of the blood. So whether it's arterial blood or venous blood, that's going to give you the total oxygen content. Okay. So you can rewrite this, like I said, for different types of blood. So if you're looking at your mixed venous blood, you're going to look at the percentage, the saturation of the O2, or your percentage saturation of O2 in the mixed venous blood, your mixed venous partial pressure of oxygen. So it's the same equation, you're just plugging in different numbers. And then the capillaries, the pulmonary capillary blood, because this is pre-shunts, So you can assume that it's 100% saturated. That's why you don't have an SO2 value here, because it's going to be 100%. So your hemoglobin times that 1.34 plus your P big AO2. So that's your partial pressure of oxygen in the alveoli, not the arteries. So this you have to calculate for. The other one, you're just going to get the number given to you off of an ABG value. This one you're going to have to calculate for, multiplied by the 0.003. Right. So to remind you how to practice or where to find these calculations in your calculations book. So I first have to calculate for this one here, which is going to mean that I have to take I'm just going to type it. It is your PaO2 is going to be equal to your barometric pressure minus your partial pressure of H2O in the lungs, which is always going to be 47. You multiply that times your FiO2. You're going to subtract your PaCO2 times 1.25. Okay, so that's how you're going to calculate that out. Right, so if you want extra practice calculating that, that's chapter 3. Chapter 3 in your calculations book, which starts on page 14. Oh God, I hate it when they do that. Okay, that starts on page 14. Okay, so extra practice with oxygen content. That is chapter 52, 53, and 54. So oops, sorry. Sorry, I need to wait for it to. So chapters 52, 53, and 54 all are going to go over oxygen content. So the last 3 slides are in your calculations book, are covered in those chapters. Or maybe it's not. Let's double check here. Let me find the page number for you. So that starts on page 173. Page 173, 2. Excuse me. 183. Okay, and that'll just give you some extra practice on these calculations if you're worried about math. All right. Excuse me. Right. So the oxygen hemoglobin association curve is really this relationship, or like an illustration of how that percentage of hemoglobin and the oxygen pressure kind of relate to each other, and how it's going to create this kind of graphical representation. So you can kind of predict how much, if you know one value, you should be able to predict the other. So this curve is going to be S-shaped, and it's going to have a steep slope in between this 10 to 60 torr, or the a PaO2 level of 10 to 60. And then there's going to be a flat portion on the top. Okay, so it looks like this. Okay, so there's a significance of kind of the shape of this curve. And I want you to kind of to talk about a little bit or try to help you visualize what's going on in the body when this happens. So, for lack of better examples, this is how I usually draw it. All right. So, the example I always use with this is imagine you're back at your eighth grade school dance. Okay. So you've got your hemoglobin over here, right? And then you've got your PaO2 down here, your oxygen dissolving in the plasma, right? So this starts increasing first, all right? So as oxygen transfers from the alveoli into the blood, this number increases first. So I end up with more and more O2 dissolved in the plasma. This number gets higher. So there's more, let's imagine, like I said, this is your eighth grade dance, and you have your hemoglobin or all the middle school boys standing up against the wall, not wanting to dance. And then your PaO2 is all of the middle school girls who are kind of crowding into the room. They're getting excited. They're talking to their friends. They want to get out there and dance. And as more and more and more of them come in, they start getting themselves more and more hyped up until finally we have enough girls in the plasma or in the dance hall. So we're talking about this kind of point right here, that now the hemoglobin and the O2 start linking arms and going out on the dance floor together, and everybody's starting to have a party. And as one couple goes out there, then more and 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 more couples go out there because peer pressure, and they realize it's just fine to hook up and run around the body or run around the dance floor together. So more and more of them kind of attach until you get to a certain point, which is right about here, or 60 tour, where the dance floor gets pretty saturated. And there's too many people out there. It's pretty saturated. So then we have this leveling off. We're not really any more couples are getting, there's not really anybody standing along the sides of the dance floor anymore. So there's no one else to hook up and go out there and boogie down. So that's my kind of lame kind of analogy or visualization. I don't know if that helps, but kind of the moral of this story is you have to have a lot of oxygen in that room. You need to have a lot of oxygen in that gymnasium during that middle school dance in order for that hemoglobin to start getting engaged and wanting to attach and having an affinity. This is the word we use in medicine, an affinity for that oxygen. Okay. So that steep part of the curve is significant because it shows you that as I get above 10 here, my affinity for oxygen greatly increases. Okay, so as I get above PaO2 of 10, my affinity for oxygen greatly increases. That hemoglobin, that oxygen are going to want to link arms, or want to go out there. They're going to want to dance. They're not going to want to let go of each other's hand. As I get above 60, though, that affinity for that oxygen, or as I drop below 60, so if I, from 10 to 60, I have a high affinity for that oxygen. But as I drop below 60, my affinity for oxygen starts to decrease. Okay, and it starts to decrease rapidly. So as I drop below 60, if I'm going this way, as girls start leaving and start getting picked up and going home, there's less and less partners for this hemoglobin, and that affinity starts dropping off, and more hemoglobin just goes and stands up against the side of the gym again and doesn't want to dance with the oxygen. Hopefully that helps. So if you think about your body, it's good because this relationship is really important because as I want my hemoglobin to attach to oxygen in the lungs and so it can get transported through the body effectively. But when I get to the tissues, I want that hemoglobin to let go of that oxygen so that then it can be diffused into the tissues, right? So in the lungs, I want a high affinity, right? So I want this affinity to be really high in the lungs um, um, where this oxygen is getting picked up. And then I want that affinity to be really low in the tissues where I'm dropping it all off. Okay. So if you think about our body has kind of built-in mechanisms to help shift this curve right and left. So a shift to the left means that I just pick this curve up, and instead of being right there, the curve has the same shape, but it needs less oxygen, right? It needs less PO2 in order for the hemoglobin to attach. A shift to the right again, same shape, but if it's shifted to the right, I need more oxygen dissolved in the plasma in order for that hemoglobin to want to attach. So if it's shifted to the right, my blood has less affinity for the oxygen. Right. So there's several factors that cause these things to shift. One of them, the first one being pH. So as my pH increases, meaning that my body is becoming more and more alkalonic. Okay, so my pH increases. That means I'm becoming more alkalinic. And that's usually happening because there's less CO2 in the blood. Um, that is going to cause the shift to the left, which is going to have, I'm going to write that up on top so we just keep everything straight. Hold on. So this one hemoglobin loves O2 when you're shifted to the left. Hemoglobin loves O2. Okay. And then when we're shifted to the right, my O2 has a broken heart. So when we're shifting to the right, that's where the hemoglobin and the O2 are breaking up. So shifts to the left, you have that increased pH, usually because your PCO2 is dropping, your carbon dioxide levels are dropping. That's what causes your pH to increase. Also in areas where you've got a decreased temperature, or in cases where you have something called BPG. This is a kind of a substance that pregnant ladies release um, so that so that their bodies uh, don't want the oxygen, so it goes to the baby instead. So So this DPG is that hormone that maternal or pregnant ladies have in their bodies that cause that right shift, because the maternal blood doesn't want to hang on to the hemoglobin very strong, or to hang on to the oxygen very strongly. It wants to drop it off at the placenta easily so that the baby can, the fetal hemoglobin, which has a strong affinity, will pick it up. Carboxyhemoglobin, which is hemoglobin that is attached to carbon monoxide, that also has a very, very, very strong affinity. So carboxyhemoglobin, carbon monoxide and hemoglobin has a super strong affinity. It's going to have like over 200 times the affinity for oxygen, than over 200 times the affinity for carbon monoxide than oxygen. So because of that, then even small amounts of CO2 are going to build up on that hemoglobin and prevent those oxygen molecules from binding and, getting transported throughout the body. Okay, so BPG, let me change my thingy here. BPG is a substance, DPG, BPG, that makes it difficult. This BPG is a substance that happens during anaerobic glycolysis, which is kind of a fancy term meaning the body didn't get the tissues, the cells didn't get the oxygen they needed to perform metabolism. So then metabolism happened without oxygen, which when that happens, we produce less ATP, less energy, and you also end up with a bunch of kind of fixed acid byproducts that are gonna increase the acidity in our bodies. So when that happens, when so when that is when that is elevated, it's going to shift the curve to the right, which is going to try to help get that uh, hemoglobin to release the oxygen to the tissue, so that anaerobic glycolysis stops or is slowed down. Okay, so talking about the clinical significance of this a little bit, if you remember this curve here, this is what it's normally supposed to look like. So if I'm shifting this curve to the right, okay, clicker pen takes a minute to always work. If I'm shifting this curve to the right, then this is extreme. I've shifted the curve over this way. Then instead of at 60 torr, meaning my PaO2 is about 60, that's normally what it should be. Well, as it's leaving the lungs, if my PaO2 ends up being about 60, that means I'm about 90% saturated with my hemoglobin. But if I've shifted to the right, at that same 60 torr, so the amount of oxygen that's dissolved in the plasma or diffused across is still the same, then my saturation is, instead of 90, it's about 75% saturated. So that drastically drops my oxygen carrying capacity by shifting it to the right. For any of those reasons that we described before, like decreased pH, increased PCO2, increased temperature, increases in that DPG. Actually, let me just go back for a second. I just wanted to make one one point here, that in these left shifts, this is how we want the blood to operate in the lungs, right? Because this is where oh, those are bad lungs. um, this is where the oxygen gets picked up. So we want a high affinity for hemoglobin and oxygen in the lungs. The right shift happens at the tissue level. That's where we want this to happen. We want things to shift to the right at the tissue level, so those hemoglobin molecules get dropped off at the tissues. Not the hemoglobin molecules, the oxygen molecules get dropped off at the tissues. Unbind from the hemoglobin and get dropped off at the tissues. So if this process is messed up for any reason, like it shifts to the right instead of the left in the lungs, then my hemoglobin is not going to be as attracted to the oxygen molecules, so I'll have less than anticipated saturation levels. Okay. If it shifts to the left, okay, which is what we want it to do, then I'm going to have more oxygen shift binding to that hemoglobin, so I'll end up with a higher oxygen saturation. So shifting it to the left is what I want to have happen in the lungs, which is going to cause that saturation to increase. So instead of being like 90%, it's going to be like 95%. Okay. So now I don't want you to lose your heads about this too much, because as you look through this chapter, like I said, there does look like there's a lot of math. There's not a lot of math I'm going to expect you to actually physically do. Okay, the oxygen content, the alveolar oxygen tension, yes, I want you to be able to do those calculations. Your pulmonary shunt calculation, I want you to be able to do that. But all of these other ones, I do not expect you to do. Okay. So when we talk about total oxygen delivery, so this is just understanding that your total oxygen delivery, what's delivered to your tissue, is kind of a product of how much actually got into the blood, so dissolved in the plasma plus bound to the hemoglobin, which makes your total oxygen content. Goodness. All right. How much, you know, and then your cardiac output. Okay, so this is your cardiac output. All right. So the things that are going to affect my total oxygen content are going to be like my hemoglobin concentration, how much actually got dissolved in the plasma, and how much actually got bound to the hemoglobin. Okay. So typically your oxygen delivery is going to decrease when anything that's affecting ventilation is causing a decrease in the availability of that oxygen in those alveoli. So if I don't get O2, if O2 stays up here and never gets down into here, then my O2 never is going to get into here, right? Okay, so that's going to cause a decrease in my overall O2 O2 content and a decrease in my O2 delivery. Change my colors here. If I don't have hemoglobin, so if hemoglobin is blocked from getting here, no hemoglobin here, then there's no relationship between this oxygen and hemoglobin. And that's going to cause a lower O2 content and a lower oxygen delivery. Okay. And then the same thing with cardiac output. So if I'm not getting a lot of, oh, I should change my color. Sorry. So if I don't have a lot of blood going past these lungs, not a lot of perfusion, again, that makes it so, I'm gonna do this as QT, just to keep consistent cardiac output. If that is low, then I don't get enough blood coming in contact with the alveoli here, or if my heart, it's a really bad heart drawing, if my heart isn't pumping out a lot of oxygenated blood, oh, I hate it when that happens. All right, so if I don't have a lot of blood coming out of here, then I don't get a lot of blood to my tissues. All right, so that would decrease. If this decreases, then your oxygen delivery also decreases. The 10 is just kind of a factor to make all of your units of measure equal. Okay, like I said, you don't have to calculate this for me. I just want you to understand the calculation so you can understand how these things contribute to it. Oh, what happened here? Holy moly. There we go. All right. So sometimes we have patients that are really clinically very sick, get a device called a pulmonary arterial catheter place. This catheter allows us to take measurements of um, the patient's mixed venous blood. So what that does for us is it kind of tells us a lot about shunting, and it tells us a lot about our patient's cardiopulmonary status, because any of those oxygen changes in that mixed venous blood can kind of demonstrate kind of oxygen nation or oxygen carrying capacity issues in the arterial blood. So typically we can use this calculation if you have that pulmonary arterial catheter in, to just assess whether or not that there is an increase in this gradient. So so if you have an increase in this gradient, meaning that the oxygen content in my arterial blood is quite a bit higher than the oxygen content in my mixed venous blood, that happens it because of either typically because of either decreased cardiac output. Oh, I should switch slides here. Um, decreased cardiac output, or because of anything that's going to increase my oxygen consumption. So meaning that my oxygen consumption is oxygen's getting used in my tissues a lot more, either because of exercise, I need to produce more energy, seizures, shivering, or hyperthermia. Things that are going to decrease my gradient are increases in cardiac output. So faster the perfusion, the better the perfusion to the body, the better the oxygen delivery, or the more available that oxygen is to the tissues, or things that are going to cause my tissues to not need a lot of oxygen, so they're not being worked. So skeletal muscular relaxation, hypothermia, slows everything down, your metabolism down. Peripheral shunting can also cause this. So, like, that happens in patients with sepsis or trauma, where blood is just not going to go to all of those tissues. So it can't go to the tissue. So the oxygen can't be used or consumed by that tissue. And then certain types of poison. So, specifically, cyanide poisoning is going to cause issues with it. Kind of prevents the oxygen from going into the tissues and being used for cellular metabolism. So that's going to decrease because it can't, that oxygen can't be dropped off and used in metabolism. It stays in the blood and it decreases that gradient. So oxygen consumption is what we talk about as the amount of oxygen that's extracted from the blood by those peripheral tissues. Okay, we're usually looking at it over like a minute of time. So it's kind of also known as oxygen uptake. So this is something that if you ever end up in pulmonary function testing or kind of a fancy pulmonary function lab, you might do exercising testing and you might calculate this a lot. But for most of us respiratory therapists, we don't. I don't think even when I worked in the PFT lab, my PFT lab was not fancy enough to do exercise testing. So we have never actually had to do this with the patient. So, if you think about it, your oxygen consumption is going to be kind of relative to the amount of tissue you have that's consuming that oxygen. So it's going to be related to your body surface area. So it's going to vary by the person's height and weight, depending on how much is appropriate. Okay, so to calculate out your oxygen consumption, again, you're looking at your cardiac output. You're looking at that gradient between the oxygen content in your arteries and your mixed venous blood. And then you're just multiplying it by 10 because that's what's necessary to make all the units of measure equal. So factors that are going to increase oxygen consumption are exercise, seizures, shivering, hyperthermia, anything that's going to make us use our muscles or use our tissues more, produce more energy. It's going to increase our oxygen consumption. Anything that is going to decrease it, again, just kind of like your gradients. Anything that's going to decrease it is that skeletal muscle relaxation, the peripheral shunting, those poisons like cyanide, and the hypothermia. Your oxygen extraction ratio, that's the amount of oxygen that's extracted by the tissues divided by the amount of oxygen delivered to the tissues. So you're going to need your ratio again, or your gradient between your arterial oxygen content and your venous oxygen content, and then you're just going to divide it by your arterial oxygen content because that's what's brought to the tissue level. Okay. So again, things that are going to increase my extraction are the same as the things that increased my consumption and increased my gradient, as well as anemia and decreased arterial oxygenation. Because if my number here is lower, that's going to increase my overall value. Things that are going to decrease the ratio are increase our cardiac output, anything that's going to increase O2 consumption. And then if I have extra hemoglobin, then I'm going to have lots of extra potential for oxygen carrying capacity, and any increases in arterial oxygenation would decrease that ratio. Okay. So I feel like this sometimes gets to be a little bit of a hard concept, this mixed venous oxygen saturation. So this is this is the kind of something that we use, again, when we have those pulmonary arterial catheters in, to evaluate or detect changes in that patient's um, oxygen content gradient, that O2 consumption, and that extraction ratio. So normally your mixed venous saturation should be about 75%. Okay. So as long as it's above 65%, that's usually considered kind of clinically acceptable. um, so things that are going to decrease your mixed venous oxygen saturation are going to be the same things that increase your oxygen extraction ratio. So decreased output, periods of increased O2 consumption. Factors that are going to increase it are your increased cardiac output, and then anything that's going to kind of relax or slow down your metabolism. All right. So I think I'm going to stop here and then talk about shunting in a part 2 video. Okay, so I'm going to stop here. This is going to be part 1, and then I will do part 2.